Hello, and welcome to the next exciting adventure where we're going to go on, called Factoring Polynomials. Yes, that's right, we're factoring. Alright, so let's jump in. So this is lesson 4.4, called Factor Polynomials. So an example of this is kind of our tradition. So we'll start here. So if you imagine a three-dimensional cube and then a little tiny cube taken out from inside of it. So there's a couple of things that we can kind of do here. Trying to find the volume of the cube. Let's zoom in a little bit. So we can find the total volume of the cube by using length times width times height. And then we could try to find the volume of the inside of the cube, that little tiny cube there, and then we can subtract the volume so that we can figure out how much this part is, or the whole thing, and how much the smaller part. The other way is that you can break it down into pieces. So kind of like what they did, and I think they've got. So you can break it down into the different pieces. So we've got A, this one right here is going to be A minus B. Then we've got A here. And then, doing that kind of rationalizing through, you can find the volume of each different piece and then just add those together. So factor polynomials. So analyze a visual model for polynomial factorization. So factoring a polynomial involves finding factors of lesser degree that can be multiplied together to produce the polynomial. So this is something that we have done a little bit with second degree polynomials. So for this guy right here, remember we look at this factor, we kind of list out our multiples of that factor. So we've got 1, 6, 2, and 3, and that's it. And then from there, we need to figure out how to get this number. And we do that by either adding or subtracting our multiples together. So our adding and subtracting is determined first by this sign, and this should be a review, but this sign, if it's positive, that means that both numbers that we're going to add together are going to have the same sign. Then we look at this sign right here, and this is going to tell us which sign that is. So this one is positive, so they're both going to have the same sign. This one is positive, both numbers are going to be positive. So now we know that. We can then figure out, we look at our different multiples here, and we're trying to add them together to get this number without the x. So just 5 in this case. So 1 plus 6 is not 5, but 2 plus 3 is 5. So typically when you're asked to factor a second degree polynomial, you set up your parentheses. So you know that this x is going to go both places. Look at this sign. That's positive. So the next one's going to be both the same. And they're both going to be positive. So you're going to put your plus, plus, and then your multiples are going to be 1. I'm sorry, not 1. I knew that was wrong. Go away 1. There you go. So we know that it's plus. So it's going to be 2 and 3. So that's generally how we factor. And that's, of course, what they got as well. So that was a quick review of just how to factor the degree 2 polynomials. If that was hard for you or you don't remember, that's okay, but make sure that you kind of review on your own to make sure that you're solid with that, because it's only going to get harder from here. So that's my word of warning. But moving on. So when a polynomial has a degree 3, so like an x cubed, you can think of the volume of a rectangular prism whose dimensions you need to determine. Dimensions are factors of the polynomial. So this is one way to visually think about it. So you've got the volume of all these different rectangular prisms, and then our total volume is just all of them added up together. So what they did right here is they gave you the volume of the red, green, yellow, and blue, and then they added them all up together and simplified. So you've got your x cubed, you've got your 2x squared, and your 4x squared. So that's where they got the 6x squared. Then you've got the 8x. So that's just one way to visually think about what we're doing. Okay, here's where we get into it. So your first step, they give you a polynomial of degree 3 or more. Your first step is going to be to factor out the greatest common factor. So real quick background, not all polynomials can be factored over the integers. That is, they cannot be rewritten using only factors with integer coefficients and constants. When a polynomial is factored, the degree of each factor is less than the degree of the polynomial. While the goal is to rewrite the polynomial as a product of linear factors, that is not always possible. A factor of degree 2 or greater that cannot be factored any further is an irreducible factor. So long story short, an irreducible factor is a polynomial that is not factorable. Too easy. So when we are factoring, though, the first step is going to be to find the greatest common factor. So the greatest common factor. Assuming it's not 1. That's not helpful. So below are two examples of factoring polynomial over the integers. So we've done this before in class, but I might not have explicitly stated it, so here it goes. So the very first thing you do when you're trying to factor something is find any common factors that you see. So I can see immediately that we have an x that is factorable out of all of those different numbers, and it looks like we have a 4. So we can take a 4x out of every single one of those. So then that's where we come up with this. We've got 4x times 2x squared minus x minus 3. So now that we have this guy right here, this is just a normal degree 2 polynomial that we should be able to factor. So the way we get to that one, get rid of some of those. So we've got 2x squared minus x minus 3. So we're going to set up our parentheses. So here we've got a coefficient. So one of the x's is going to have to be squared. So 2x and our x. So that means that our factors over here, so with this guy, so we've got 1 and 3. So that's kind of useful. That's the only two factors that 3 has because it's prime. But one of these numbers is going to be multiplied by our 2 before it gets added together. So let's continue through the steps though, and we'll hit that. So we look at this sign right here. That sign tells us that we are going to have a plus and a minus. And when we add the 2 together, we're going to get a minus sign. So that means that one of these two numbers is, number one, going to be negative, number two, going to be multiplied by 2, and then when we add them together, we're going to get negative 1 out of that. So, just, I don't know, my brain can kind of come up with it from this next part, but if we take 3 minus 2, that's going to be 1, but that's not right. We want a negative 1. So that means we're going to take negative 3 plus 2. So if we do negative 3 plus 2 times 1, that's going to give us our negative 1. So that takes care of this 2 and our 2 signs. So let's get rid of some of those circles. So that means that since the 1 is going to be multiplied by the 2 from up here, so the 1 goes over here, we need the 3 to be negative, so we're going to put minus 3 here, and that's going to be our plus. So, again, I'm sometimes not good at this, so I'm just going to double check real quick, and that's when we start foiling. So 2x times x is going to be 2x squared. 2x times 1 is going to be plus 2x minus 3x minus 3. So then that's going to be 2x squared minus x minus 3, which is the same thing that we have up here. That is how you can check to make sure that your factoring is correct. Also, it helps that the book gives us the answer as well. But, whatever. So again, if you struggle a little bit on factoring, that's okay, but that's a skill that you're going to need this chapter, or this lesson. So how do you know that the greatest common factor is 4x? What I was looking for, number one, I immediately saw the x, so okay, that one's easy. And then I looked at this 4. That is the biggest number that we could possibly take out, and that's not even a guarantee. But I went ahead and I tried that, and so 4 can come out of 8, 4 can come out of 12, so we just took a 4x. So that was kind of what was going on in my head when I was trying to figure that out. So our next example. So we've got 3x cubed and 21x. So again, I already see an x and an x, so we're going to pull that out. And then our greatest factor, our greatest coefficient, is that 3. So I kind of, in my brain, I always start with, well, is that going to come out? So 3 divided by 21, it will come out. So then we have our 3x times the quantity of x squared minus 7. So 3x cubed divided by 3x is x squared. Negative 21 divided by 3x is negative 7. So that's where all of that came from. So, and that's as far as this will go. We can't take it any further. So it is totally factored, if you will. So they've got a couple questions. Why can't you factor x squared minus 7 over the integers, but you could factor x squared minus 9? So x squared minus 9 is the difference of two perfect squares. And so there is a pattern for that. So x squared minus 9 is the difference of two perfect squares, also known as x squared minus 3 squared. And there's a pattern for that of x plus 3, x minus 3. So this is, again, the difference of perfect squares. That's something, if you don't remember, you probably need to do a review for that, because you're going to need that. And let's see here. Explain why it is possible to factor x squared minus 7 over the real numbers, but not over the integers. So you can't pull an integer out of here except for 1, and 1 is not helpful. So whatever. So we just mentioned a pattern with the difference of two perfect squares. So in the same way, there are some common patterns with degree of 3 polynomials. So that's what we're going to kind of look at. So here's our pattern of difference of two squares. And that's if you have a squared minus b squared. Perfect square trinomials. So again, a squared plus 2ab plus b squared is going to equal to a plus b squared. And then you have that minus sign. You can do a minus b squared. Minus b quantity squared, I should say. And the sum of the two cubes. So there you go. You can pull out just an a plus b, and then you have this left over. And generally this is going to be factorable even further. Same with the minus sign. So again, I'm a big proponent of not memorizing things, and I will not force you to memorize these things. However, I can put this on the board, but if your brain doesn't recognize these things as you're working through the problems, then it's not going to do you much good. So if you're going to study anything, study this and know this inside and out. Even if you don't remember this side of the equation, you will need to recognize these things as you are working through the problem. So really think about that and make sure that you are trying to recognize those. So let's try a problem out. So here it says factor 8x cubed plus 125. So immediately I'm thinking, I wonder if this is the sum of two cubes. So I've got a cubed here, and 8 I can figure out in my head. 2 times 2 is 4. 4 times 2 is 8. So, whoops, didn't want to do that. So this is really like 2x cubed. Man, and I wonder if this is a cube. So again, I'm thinking in my head, how do I figure out if that's a cube? So I'm just going to kind of start guessing and checking. So I see, number one, it's odd, so 2, 4, those are kind of out. But I see this 5. So let's try that. I'm literally going to pull out a calculator, and I'm just kind of guessing. I wonder what 5 to the power of 3 is. Hey, look, turns out 5 cubed is 125. So again, I don't have that memorized, but I just kind of rationalize it out, and you have to try to pick up on these things. So that is 5 cubed. So now we have a cubed plus b cubed. So now that's going to all equal, and I'm just following this formula right here, a plus b, so 2x plus 5, a squared, 2x squared, minus ab, 2x times 5, plus b squared, 5 squared. And so then you can multiply that out. 2x plus 5, so that just stays there. 2x squared is 4x squared minus 10x plus 25. So that is how you factor that guy. And I'm currently trying to think if this is factorable anymore, and I don't think that it is. Also, the book stops there as well, so I assume it's probably not. As I was thinking about it, but just so that you guys are tracking what's kind of in my head, I was thinking about this one. That's 5 times 5. It's really the only one, or 1 in 25. But we had this 4 here, so, 5 plus 5 is 10, but, or I guess negative 5 is negative 10. we have this 4, so that's going to be like 20 minus 5, so that's not going to work. 25, if I times the 25 by 4, that's going to be a super big number, and it's going to be harder to get to negative 10. So if the 4 goes with the 1, the 25 minus 4 is still not going to be 10. So that's what was kind of going through my head, and that's what's kind of need to start going through your head of like, man, how can I factor that? In this case, it's not factorable. So here's our final answer. So which factoring patterns you use in the second step? That was the this guy up here, sum of two cubes. We had kind of talked about that already. And how can you check that this factorization is correct? You can always check your factorization by multiplying it out and making sure that you get your beginning. So no matter what factoring you use, you can always check your work by multiplying it out and making sure that you get what's at the beginning. It takes a little bit extra time, but especially, I know I'm not confident about that sometimes, so I always like to check my work if I have time. So the third step in factoring our degree 3 polynomials is factor by grouping. So remember, step 1 is find the greatest common factor, pull it out, use the distributive property, pull it out. Number 2 is we then went over some of the common or typical patterns that you might see. And so number 3, you can also try factoring by grouping. So this is where you can see that it can get a little challenging at times because there's no one single set way of factoring. You kind of gotta, this is where I really enjoy math because it turns into a puzzle that you have to figure out. So factor by grouping, if you can group together pairs of terms of a polynomial that have a common factor, you may be able to use a method called factoring by grouping to factor the polynomial. The pattern for this method is shown. So it's something like this. If you have RA plus RB plus SA plus SB, you'll notice that there's an A plus B here and an A plus B. So that's what they're going to try to do. So you group the first step together, pull an R out. You group the second one together, pull an S out. And then you have R times A plus B, S times A plus B. So then, again, you use the distributive property, and you can pull out an A plus B, then you have R plus S times A plus B. So let's try a real example. So factor this polynomial. So we've got x to the 4th minus x cubed minus 8x plus 8. So I immediately see a pattern that we have two 8s here. Okay, so that might be useful. So we're probably going to end up grouping those two together. And we'll just keep this negative sign with that negative 8 so that we don't have any weird distributive stuff happening, for now at least. So then if I group my other two together, there's an x cubed that can be pulled out of there. So let's do that. Let's see what happens. So we've got an x cubed, we got x minus 1, and then here we're going to pull an 8 out. So plus 8 times negative x plus 1. Man, we're really close, except our negative signs are off. So we can probably pull, instead of a positive 8, let's pull a negative 8, and then all of our negative signs will switch. So we pull a negative 8, so now we've got a positive x minus 1. Now we've got two factors that are similar, so we're going to factor those out. So then we have x cubed minus 8 times x minus 1. And hey, while we're at it, do you remember the x cubed? Or the cubed, the difference of cubes? So we've got x cubed here, and then 2 cubed here, right? 2 times 2 is 4, times 2 is 8. So then we can use that pattern again, and let's see here. So that pattern is right here. So that's where we get the x minus 2. So that's kind of like the a minus b. And then a squared, or in this case x squared, 2ab. So that's 2x. And then 2 squared is 4. Then we have x minus 1. So we are looking at this guy, thinking, okay, can we factor that? 4's got a couple of factors, 1 and 4, 2 times 2. Unfortunately, you can't add or subtract any of those in any combination to get that 2. So we are fully factored. And standard notation, you pull all of these guys to the front. Doesn't necessarily matter what order you go into, but whatever. So, and they've got the x minus 1, x minus 2, x squared plus 2x plus 4. So we were able to factor 2 factors out of that, first by grouping and then by using one of our patterns. So what property justifies? Most of this stuff is the distributive property. If you move stuff around, that's the commutative property. And how do you know that the polynomial x squared plus 2x plus 4 is irreducible? So we kind of talked about that. We looked at the multiples here, and we could not get them to add up or subtract up to anything like that. So that's how I knew it was irreducible. All right, we're going to do another example. So it says factor by grouping, and it gives us the polynomial. And I'm going to tell you that there is a typo here. So that 8x should actually be squared. So I figured that out the hard way, but you don't have to. So what we've got here is 4x cubed plus 8x squared minus 9x minus 18. So they kind of have the habit of putting things together for us. Makes it a little bit easier, but don't rely on that. So if we look at these first two, there is an x squared definitely together, or that they both have together, and then we could also take a 4. So that's going to be a 4x squared on the outside, and then we're going to have x plus 2. So over here, I'm willing to bet that number one, we're going to have to take out a negative sign, because this x plus 2 is a positive x plus 2. So these are both negative, so that's kind of why I'm thinking we're taking a negative sign out. And they both have a 9 in common, so we're going to take that 9 out, and then we will have x plus 2. So here we go, we've got x plus 2, x plus 2. So the distributive property at work. Or I kind of think about it as you're factoring an x plus 2 out. So you're going to have 4x squared minus 9 times x plus 2. So hopefully right now some bells and whistles are going off about this guy right here. So I'm going to bring that one up over here. 4x squared minus 9, just him by itself, because this is the difference of two squares. So if you remember, there is a pattern that goes along with it. I went ahead and screenshotted that table that they gave us because I get all of these patterns confused. So that's why I mentioned it's probably very important for you to be able to recognize these sides of the equations, and then you can always just pull that up. So I've got difference of squares, difference of two squares, a squared minus b squared, that's what I've got. My a is 2x, my b is 3, because 9 is also equal to 3 squared. So then that is going to factor into 2x plus 3, 2x minus 3. So then we can come back over to the right side, and we're going to continue factoring. So we've got 2x plus 3, 2x minus 3, and then x plus 2. So that's how you're going to factor this guy. As you've seen, or as we went through, there's definitely multiple steps, and you're going to start using all of these things together that we've learned about factoring. So this next part is just trying to get everything in order for them, but we went through the process and we successfully factored it. So there we go. Alright, we got one more to go. So this is factor polynomial to solve a real world problem, aka a word problem. So we've got a landscape architect is designing a marble flower planter for an outdoor mall. The planter should hold 4 cubic feet of soil. The architect wants the length of the planter to be 6 times the height and the width of the planter to be 3 times the height. The sides of the planter should be 1 foot thick. Because the planter will be on a sidewalk, it does not need a bottom. What should the outer dimensions of the planter be? So if you look at this picture right here, kind of gives us everything that I just read. So the height is going to be x. And then we've got the length here, length there, and that's going to be 1 foot. So we're going to use our verbal model. And let's see here. It said 4 cubic feet. So that means that this inside here is going to have a volume of 4 cubic feet. So we know that we're going to be finding a volume, which is length times width times height. But we need the volume of this inside little part based on x. Once we find x, once we solve for x, then we can plug it in here and we can find the length and all sorts of other whatever questions they have for us. So our length times width times height for this inside here, the length is going to be this total length here minus our 1 foot and minus our 1 foot. So our length is going to be 6x minus 2. Okay, so we use that same logic to find the width. So let me scroll up here a little bit. So our width right here is again 3x, but we've got 1 foot there and 1 foot there. So that's going to be 3x minus 2. And then the height is just x, because the height, we don't need a bottom, so the height in the middle is going to be the same as the outside. So there is our initial equation, and we can say that it equals 4, because it said the planter should hold 4 cubic feet of soil, or dirt. Don't let a soil scientist hear you call it dirt. So just to make sure, this is what they've got. They've got our 6x minus 2, 3x minus 2, x equals 4 feet. So here we have our equation. So in order to solve this, we first need it to actually equal 0. But in order to get this 4, now, I mean, just to get it to equal 0, we just subtract 4 from both sides, right? But then we're going to have some factor, and then minus a thing. So we don't really know how to do that. So the process for this is we're going to multiply all of this out, combine like terms that include the 4, and then refactor it with this 4 built into the equation. So it seems like it might seem like a lot of steps, and it kind of is, but that's the only way that we can get this 4 incorporated into that equation. So here we go. Okay, get that out of the way. So we've got, I'm just going to FOIL this straight up. And then, so that means that we've got 6x times 3x, 18x squared minus 12x minus 6x plus 4. And then we're just going to add another x into everything. So that's going to be x cubed, x squared, and x equals 4. So I just added or multiplied that x by everything. So that's where I got that. So then we combine like terms. 18x cubed minus 18x squared plus 4x, and then I'm just going to subtract 4 from both sides so that I have minus 4 equals 0. So I did several steps right there, but here we are if you're following along in the book. So from there, again, it kind of sort of ended up being grouped for us, which is convenient. So in here we've got an 18x squared in both factors, so that's what we're going to take out. So we've got an 18x squared on the outside. That's going to be 1x left over minus 1. And then here we've got a 4 in both factors, so we're going to factor a 4 out. X minus 1 equals 0. Hey, look! X minus 1. Imagine that. So then we've got 18x squared plus 4 times x minus 1 equals 0. So hopefully this is ringing a bell. That is the, let's see here, I think, is 18 a perfect square? I don't think it is. Here I was so excited that we were going to have the perfect square. 18... Yeah, I don't think it is a perfect square. Well, I was getting all excited about that, but guess not. So then I'm going to come down here and check this, and this is as far as they got it as well. So I got excited for nothing. That's a shame. So anyway, in order to solve this, just like you would a normal equation, you're going to set this equal to 0. Then you're going to set this equal to 0, and those are going to be your x's. So our first one is x equals 1. That's from that guy. And then this one 18x squared plus 4 equals 0. So we're going to solve that. Minus 4 from both sides. So then we're going to have 18x squared equals negative 4. X squared equals negative 4 over 18. Which is equal to negative 2 over 9. So then we've got x squared equals negative 2 over 9. So then we're going to bring this right up here. So we've got x squared equals negative 2 over 9. So then we're going to square root both sides, which this is also going to equal, we'll pull the I right out, so we got a negative sign under there. I, square root of 2 on top, square root of 9 on bottom. So then x is going to equal plus or minus I square root of 2 over 3, because the square root of 9 is 3. Or, yeah, so that's our equation there. I'm going to go out on a limb and say, since we're in the real world, I doubt that this is going to be useful for us, because how do you have an imaginary length or even a negative length? So I have a feeling that our answer is going to be the x equals 1. So let's see what the book tells us. So there's our answers down here. Same ones that we got. So we did factor by grouping. And then that was really all that we could do. Okay, this is just justification. Why do the solutions x equals plus or minus square root of negative 2 over 9 not make sense in this situation? So we talked about that. We're in the real world. We're talking about an actual physical length. You can't have an imaginary length. So, since x is the planter's height, the only solution that makes sense is x equals 1. So now that we know that, or now that we found that x equals 1, to actually answer the real question, what should the outer dimension of the planter be, we're going to plug it into this guy and this guy, which is pretty easy because x equals 1. So then we're going to have a planter that is 6 feet by 3 feet. And again, I just plugged in a number 1 for those x's. So there we go. Good job.